Hello everyone. In this lecture video, we will discuss our third uh, iterative method, and this is called secant method. Okay, so let's go now to our slide. So as you can see here, uh, this is the previous method that we discussed. So we are now in secant method. So this is the slide for the secant method. It says here, one drawback of Newton's method is that we need to know the first derivative explicitly to evaluate f prime of p sub n minus 1 in this formula. Okay, if you don't know how to get the first derivative of the function, especially if the function is hard to get the first derivative, if it is defined implicitly, then it will be hard for you to perform the Newton's method. So for this, we will use a second method. So if we don't know the first derivative explicitly, or if its computation is expensive, just like I've said before, we might approximate the first derivative by the finite difference. This one. This is formula 2.11. Formula 2.11. This finite difference. It's easy to get. Okay, just use the if you remember in your calculus 1. So let's go to our open board. Okay, let's go to the open board, and for example, if you have a function like this one here, so let's make a x-axis and y-axis. As you can see here, let's make a line somewhere here. Okay, that's the x-axis and also the y-axis. Okay, so for example, y-axis, and this is our x-axis. And what if you have a function, let's say this one here, this function. Okay, this is your function f of x. Okay, and then notice that if we get the derivative, let's say this one here, okay, this tangent line. Okay, if you have a tangent line here in this point, so if we approximate the first derivative by the finite difference, so what does this mean? Okay, so for example, if go back to our open board, if this is your p sub n, okay, if this is your p sub n minus 1, okay, and this is your p sub n minus 1 plus h, okay, plus h. So to approximate the first derivative, f of this is f prime of p sub n minus 1, so you will use the finite difference. Okay, so this is f of p sub n minus 1 plus h. Okay, so using this, you will have to write this one as let's use this color. The numerator is f of p sub n minus 1 plus h minus, notice that this point here, this point is p sub n minus 1 plus h comma f of p sub n minus 1 plus h, and this point is p sub n minus 1 f of derivative is somewhere here. Okay, that one, it's a it is a line slope. Okay, so f that point is this is the derivative, this one. Okay, f of p sub n minus 1. Okay, so this is f of p sub n minus 1 over the denominator is right minus left, p sub n minus 1 plus h minus p sub n minus 1. Okay, so you can cancel out this one here. So that's why we have the formula. If you look at our PDF, okay, this is the approximation of the first derivative by the finite difference, this one. So this is how we get this formula based on the graph that I have shown you in the open board for some small h. Okay, so we need to compute two values of f at each iteration to approximate f prime. Unlike in the Newton's method, you will have to one value for the initial guess and then the first derivative. Unlike in the second method, you don't need the first derivative. Okay, so since if f prime, if you do not know the derivative of the f prime, or if the computation is very expensive or very long, then one way to get that out is using the second method. So determining h in this formula brings some difficulty, this one here, but there is a way to get around this. We will use the iterates themselves to rewrite the finite difference in 2.11, equation 2.11. So what will have the iterates p sub n minus 1 and p sub n minus 2. So what we will do here, if you look at the open board, so instead of using this finite difference, you can use the iterate. So you will replace p sub n minus 1 plus h by p sub n minus 1, and p sub n minus 1 be p sub n minus 2, or the other way around. It doesn't matter. So just like the way that we get this formula here, so all you have to do is to plug into the function. Okay, so this is the new what do you call this one, ordered pair. We will replace this ordered pair by p sub n minus 1 comma f of p sub n minus 1, and also you have to replace this one by p sub n minus 2, since we already replace the points in the x-axis, the iterates, this one here, the two iterates as this point. Okay, since h is really hard to evaluate or to get. Okay, so just like getting this slope, you will use this one here. So the ordinate minus ordinate the ordinate of this point minus the ordinate of this point, and the abscissa of this point here minus the abscissa of this point here is what we have in the formula. Okay, so our new formula is f of p sub n minus 1 minus f of p sub n minus 2 over p sub n minus 1 minus p sub n minus 2. So this is now our new formula. Okay, so if we go back to our slide, okay, so this is the recursion for p sub n if simplified. So just like the formula for the Newton's method, all you have to do is to replace the denominator by the one that we get, this one here. Okay, so replace. So the first derivative in the denominator in the Newton's method formula by this one here. So after simplifying, you will have this formula for the second method. So what we observe here is that the new recursion for formula for the second method don't require the first derivative, so no additional function evaluations are needed. So all you have to do is to plug in the two iterates, p sub n minus 1 and p sub n minus 2, to the function, and it requires two initial guesses. Okay, p sub 0 and p sub 1. Of course, n is greater than or equal to 2, so meaning to say when n is equal to 0 and when n is equal to 1, it should be the initial guess of the recursion formula for the second method. So the geometric interpretation, just like before, this one here, the slope of the second line, this point, based on our computation in the open board, this one here, okay, based on our computation, this is the slope of the second line. So go back to our PDF. So this is the slope, and the x-intercept of the second line, which is set to be p sub n, this one here. So just substitute, and you will get this formula. So this one here, and this is for the next iterate. Okay, the next iterate. Since p sub n is on the x-axis. Okay, so if you look at the open board, for example, this is your p sub n, this is the root. Notice that this is our root. Okay, so if we, for example, to put a dot here, this is the root. Okay, that's the root. So if this is our let's say this is our p sub n, okay, so this point is p sub n minus 1 comma 0, and this point here is p sub n f of p sub n. Okay, so if you look at our formula in, okay, this one here, so p sub n minus, look at this one here, this point. Okay, so this point, which is this one here, sorry, this point is this one. Okay, 0 minus that one. Okay, so go back to our PDF. 0 minus that one, and then in the x-axis we have the x-axis we have this one here, p sub, sorry, this must be p sub n, sorry, that must be p sub n. So p sub n minus p sub n minus 1, so this should be p sub n, sorry. Okay, p sub n. Okay, p sub n. Okay, so based on the formula, this one here, you can simplify the x-intercept of the second line, which is set to p sub n, this one here. Okay, so after simplification you will have this formula, which is the same as this one here. Okay, so this is the recursion for the second method. Don't forget this formula, this one here. Okay, the following theorem shows that if the initial guesses are good, the second method has superlinear convergence. So the second method, don't forget, has the superlinear convergence. For the Newton's method, we have quadratic convergence, and for the bisection method, we have linear convergence. Okay, so a proof can be found in Atkinson. So anyway, I found a book from where I locate the proof of this theorem 34. Anyway, I will not prove this one, but this will help to show you why is it the second method has the superlinear convergence. Of course, since r sub 1 here is 0.62, no, r sub 0, this is our alpha, is 1.62, then this is greater than 1, so this is the reason why we have the superlinear convergence. So anyway, we will not going to prove this, but you can go to this book, and let's try now to have an example. Before we go to the Python code for the second method, let me illustrate how the second method works by using example 36. So it says here, before we go to the Python code, let's compute this by hand. So we are going to find the solution of this equation, sine x minus e to the x. Okay, sorry, I will not solve this by hand because this is very lengthy. I will give another example before we are going to use the second and the Newton's method Python codes for this example. So let me give to you an example which is easy to follow. So let's go to our open board first. Okay, open board, and then let me have a new page somewhere here. So let's have this example. Okay, this one here, we have a function f of x is equal to cosine x minus x, and the iterates p sub 0 and p sub 1, which in which you will need in 0.5 here, and this is 1. Okay, so that's the given. Okay, of course the tolerance is EPS is 1 times 10 to the negative 4, and our n is 20. But anyway, we will use these two assumptions in the Python code for the second method. So let's compute this first by hand. So let me put this recall here, recall of the formula for the second method. We have p sub n is equal to p sub n minus 1, which is almost the same with the Newton's method. F of p sub n minus 1 times p sub n minus 1 minus p sub n minus 2 over f of p sub n minus 1 minus f of p sub n minus 2. Okay, this is the formula for the second method. Okay, so we will use that formula. So for example, remember that our n here is starts with n greater than or equal to 2. Okay, so sorry for that. Okay, so let's have here n is equal to 2. So we have p sub n, p sub 2. P sub 2, just substitute to the formula, this one here. N is equal to 2. So p sub 2 is equal to p sub 1 minus f of p sub 1 times the quantity p sub 1 minus p sub 0 over f of p sub 1 minus f of p sub 0. Okay, so this is why we need two guesses. Okay, p sub 1 and p sub 0. So just plug in the values. We have p sub 1 is 1 minus f of 1 times, we have p sub 1 is 1 minus p sub 0 is 0.5, and then f of p sub 1 is 1 minus f of 0. Okay, so let's compute. Okay, so here we have 1 minus f of, let's compute what is f of 0 here. Okay, somewhere here f of 0, f of p sub 0, and f of p sub 1. Okay, so f of p sub 0 is 0.5. Here is f of 1. This is cosine of 0.5 minus 0.5. And here we have cosine 1 minus 1. Okay, so if you go to our graphing calculator, let's go to our graphing calculator. Let's search for our graphing calculator, Desmos graphing calculator, scientific calculator, this one here. Okay, and then we use the region mode. Okay, don't forget that we will use the region mode, because in our Desmos graphing calculator, not the scientific, it use region mode. So, but before that, let's graph the function cosine x minus x. So clearly it has a root at this point. I don't know if, but it's 0.739. Okay, this is the root, approximate to 3 decimal place. So anyway, let's go to this one here. Let's type cosine 0.5 minus 0.5. Okay, so can we put a parenthesis here? So the answer is enter 0.37. Okay, so 3775. Go to our open board. That's 0.3775. Let me look my notes. We have 58 25619. Okay, so let's go back again to our, okay, 3775 825 619. Okay, and then we have cosine of 1. Copy. Cosine of 1 minus 1. Enter. So that's negative 0.45969 and so on and so forth. So let's copy that in our open board. So we have negative 0.45996976941. Okay, so that's our f of 1. So if you plug in these values to this one here, we have f of 1 is negative 0.459969769 and then 41 times the quantity here. 1 minus 0.5 is 0.5, and then f of 1 is negative 0.45969 76941 minus our f of 0 is 0.3775825 619. Okay, so the answer is you can go to our this most scientific calculator. Okay, this one here. You can type 1 minus our f of 1 is this one here, negative. Okay, copy and then put a parenthesis somewhere here and paste, times the numerator is 0.5 divided by f of 1. F of 1 is this one here. Let's copy that one, copy, and then put a parenthesis, paste, minus this is our f of 0. Okay, paste and hit enter. So what's the value? Cosine 1. Okay, so the answer is 0.725. okay, 0.725. Where's my this one here? 725. Let's go to our open board. 0.725 uh, 481 uh, 5871 5871. Okay, so that's our next iterate. We have p of 0. Okay, so that's our p2. Okay, to get the second line, notice that from here we have the point 0.5 comma 0.37758 25619, and also we have the point 1 and the negative 0.45 969 76941. Okay, so if you want to plot this, the second line, you will have, okay, this is, use this formula, y minus say y1 is equal to m x minus x sub 1. So this is very basic in calculus 1. So we will use this one here. This is our y1 x1 and then y2 x2. Okay, so just plug in here. Y minus y1 is 0.3775 8.25619 is equal to our m is y sub 2 minus y sub 1 y sub 2 negative 0.45 969 769 41 minus y1 is 0.377. So we have to write it all because there will be a huge error if we miss some digits. 8.25619 over x sub 2. Our x sub 2 is 1 minus 0.5. 1 minus 0.5. And here we have x minus x sub 1 is, where's our x sub 1? X sub 1 is 0.5. Okay, this one here, 0.5. So by in plotting, you have to transpose y sub 1 to the left side. Okay, so let's try to graph that one. Okay, let's go now to our Desmos graphing calculator, this one here. Let's try this one here, our f2. This one negative, let's plot this one first, negative minus this one. Okay, so f3 negative, this one here, copy. Let's put over first, 1 minus 0.5, and then in the numerator we have minus, let's get this one first, we have negative here, and then 0.33, copy, 377, sorry, 377, paste, and then we have to multiply by the quantity x minus, okay, based on the one here, 0.5. Okay, 0.5. Let's go to our Here is 0.5. Okay, and then close, and then we transpose F2. Let's transpose this one negative, this one here, it becomes positive on the left side. Okay, so let's go to our Firefox or this Moscow calculator. We have here positive, and copy this one here, copy. Okay, so we have to paste. Okay, and hit enter. So this is the graph of the second line, the green one. Okay, so clearly when x is equal to, when p1, notice that our iterates, our guess, we have 0.5 somewhere here, this one, this point. So the point is somewhere here, and for 1 the point is somewhere here. So this is clearly a second line because it touches the graph, the blue one, twice. Okay, so that's for that's how to graph the second line for the initial guess p sub 0 and p sub 1. Okay, so let's go back to our open board. Okay, this one here. So the next iterate is 0.725481. Okay, this is our next iterate. So notice that 0.725, if we go to our Bismos graphing calculator, our root is this one here, 7255 something, 73 something, 73, this one here, it's almost close, 7255. Okay, I don't know if that's the correct, but it's almost close to the root. Okay, anyway, let's go now to our next this one here, color n is equal to color blue, n is equal to 3. So let's have 3 more. Okay, this is p sub 3 is equal to p sub 2 minus f of p sub 2 times the quantity p sub 2 minus p sub 1, f of p sub 2 minus f of p sub 1. Okay, so our p sub 2 is 0.725481571 minus f of p sub 2. So what is f of p sub 2? Okay, we go to our this small scientific calculator, this one here, copy, paste, and then this is our p sub 2. Let's copy that one. Okay, paste and paste here. Okay, so answer is 0.022. so let's go to our open board, 0.022, 0.022, 698 39061. Okay, so and then our p sub 2 is 0.725481 5871 minus our p sub 1 is here. Okay, that's our p sub 1. Okay, p sub 1 is 1. F of p sub 2 is again 0.0226983961 minus our f of p sub 1. Where is our f of p sub 1? This one here. Okay, so we have negative 0, so this becomes positive. Okay, 0.4596976 941. Okay, so the same process, use our this small scientific calculator, this one here, copy this one and then paste it here. Okay, and then replace. Okay, so first you have p sub 2. Okay, what is our p sub 2 is this one here. Okay, that one, copy and then place it somewhere here, and then f of p sub 2, f of p sub 2 is 0.22, 0.022. Okay, 0.02 is this one here. Copy and then plug in here, and then the numerator is 0.725 p sub 2, p sub 2, this one here. Copy minus 1, our p sub 1 is 1. Okay, and then our f of p sub 2 is this one here. Copy and paste, and our f of 1, where's our f of 1? F of 1 is this one. Okay, so this one here, copy. So this is positive. Okay, positive 0.45 and hit enter. Okay, so this is our p sub 3. Okay, so that's our p sub 3. So let me copy that one in our open board. Okay, 0.738 0.738 398 and then 6201. Okay, so this is our what you call this one, p sub 3. Note that the root, I will put it somewhere here. The root based on the second method is 0.739 085 132 900 900112. Okay, based on the Python code for the second method, but we will do that one later. So let's compute it by hand. So it's almost close. 738, we have 739. So maybe if you proceed to n is equal to 4, so n is equal to 4, this one here, p sub 4 is equal to p sub 3 minus f of p sub 3 times p sub 3 minus p sub 2 f of p sub 3 minus f of p sub 2. So if you try to compute this, so to make so as not to make this video long, I'm going to put the value for p sub 4 and of course for p sub 5. So all you have to do is uh, to what do you call this one, to perform the evaluation, the computation uh, of this expression on the left hand side, no, the right hand side in the this most scientific calculator, and do the same also for n is equal to 5. So this is the formula for n is equal to 5, p sub 4 minus f of p sub 4 times the quantity p sub 4 minus p sub 3 f of p sub 4 minus f of p sub 3. Okay, so I will compute this and then secretly, and then I will put the value of p sub 4 and p sub 5 here, so that the video will not be long. Okay, so I'm going to pause this first and then proceed to the computation in uh, secretly. Okay, and I will come back later. Okay, so this is the result of the computation that I did while I was computing it in the Dismos scientific calculator. So for p sub 4, I computed the value. If you look at here in the browser, Firefox browser, so what you will see there is that you will have let me put my Oyon first, and then for p sub 4 the answer is 0.739,087,2108, this one here. And for p sub 5 is 0.739,085,1329. So this is the computation, this one here. Okay, and also this one also. So let me put it here. 0. So this is 0.739 0872108. Okay, for p sub 4. And for p sub 5, my answer is, I hope we have the same calculation, 7390851,329. So I'm going to ask these two results in Edpuzzle if you have done it in your respective home. And also I'm going to ask in the Edpuzzle the second line for n is equal to 3 and n is equal to 4 and n is equal to 5. Okay, just like this one here. Okay, so that you will see it in the Dismos graphing calculator, the graph of those lines, and you will see that it will really converge to the root 0. What's that? 0.73. Where's that one? 739,085,1329,0012. So after 4 iterations, first iteration is this one, 1, 2, 3, 4, you will have as much as possible close to this value. One, notice the what you call this one here, the last digit 1329, based on our root in the Python code for second method. We have this one here, the remaining is this one here, digit 0012. The reason for that is based on our calculation in the Dismo scientific calculator, we only have up to how many digits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 digits. Okay, so in the edpaso, I'm going to add to ask the second line, this one here. Okay, so second line for n is equal to 3, n is equal to 4, and n is equal to 5. Okay, so that's how you are going to calculate by hand the iterates for this example. Cosine x minus x, okay, to find the root. Okay, so now we are ready to type the Python code for the second method. Let's go to our PDF. Okay, this one here, Python code for the second method. Okay, ideally this one here. So we will open, and also we will try to run this problem, example 36, and also you can do a calculation, hand calculation for example 36 if you want to verify if this method, okay, really works. Okay, and then after this we will have the problem set, but before that, let's code the Python code for the second method. Okay, this is the Python code for the second method. So this is based on equation 2.12. So as you can see here, equation 2.12, this one, this formula. So we will encode this in the in Python. And notice that the initial guess is denoted by p sub 0 or p0, and p sub 1 is this one, p1 on the code. And also we put a stopping criterion as in the Newton's method. And notice also that once the new iterate p is computed, p1 is updated as p, and p sub 0 or p0 is updated as p1. So let's open now our Python IDLE. So let's have this one here and open our Python IDLE. Sorry, this one. Okay, and let's open our file, a new file. And don't forget, first is to import our package. So we have here import numpy as np, and then we will define our function, and we will call this one as secant. And we have these 4 parameters: p0, p1, p sub 1, and then eps, the tolerance and the number of iterations. So we will start at n is equal to 1 for the while loop, and also we will set p is equal to 0 to ensure the value p carries out of the while loop. So while n is less than or equal to big N, so the formula p sub n is equal to p sub n minus 1 minus f of n minus 1 times the quantity p sub n minus 1 minus p sub n minus 2 over f of p sub n minus 1 minus f of p sub n minus 2. So this is the code. P1 minus our function f of P1, remember that's our p sub n minus 1 times the quantity P1 p sub 1 minus P0 over f of P1 minus f of P0. P1 P0. And we have to put the stopping criterion if NP that is close, f of p comma 0 they are equal, or if the absolute value of p minus p1 is less than the tolerance, then you have to print that is true. Print this one here. P is, remember that this statement here says that this is in the or conjunction. So if you refer your this topic in fundamentals of mathematics, this is false if the component is false. Otherwise, if one is true, or true true, or true false, or false true, then this is true. So P is P, and the creation using okay. So if this is true, if this is false, okay, then that this no, this is true, then it will print this statement. Otherwise, you are going to return, and then you will set P0 to P1, and P1 is set to P, just like in the what I said while ago. And you will do this, up to n iterations. Okay, so after that you will evaluate this one and print this statement. Method did not converge the last iteration gives n with function value y. Okay, so this is the code. Did not space here. So, and then let's save this one first. Okay, second, save. Okay, so let's try the code. Let's try the subspace sum. Okay, let's try this code. Let's define the function, the one that we did before. F equals lambda x. First is let's import numpy as np, and then cosine x minus x, that one. Okay, and then let's call the function secant f comma, so this is our function f, and then our p sub 0 is 0.5, and then our p sub 1 is 1, and the tolerance is 1 times 10 to the negative 4, and then the iteration is 20. Okay, so if you look at our open board, you look at the open board, so we have here this one. Okay, so our root is 0.739085132 900,112. So let's go back to our F, or this one here, ideally, then hit enter. So we have here 4 iterations, and exactly the root is this one, 0.739085132 900,112. Okay, so that's for our computations in the open board. Okay, so we look at the open board, this one here. Okay, so after this is 1, 2, 3, 4. There are 4 iterations. Let's try our function in example sorry, example 36, this one. Use the Python codes for secant and Newton's methods to find solutions for this function. F of x is equal to sine x minus e to the x. So between 0 and 1. So let's try first for the secant. 0, 0 for the 0, 1, this one here for the secant method. Tolerance is 1 times 10 to the negative 4. So let's go to our code. This one here. Sorry. This one. So let's define our function. Let's say g equals lambda. Lambda x np that sine x minus np that exponential is in np times xp to the negative x. Okay, let's hit this one, enter, and let's copy this one first. Copy. Okay, so based on our this one here, we have 0, 1. Okay, 0, 1. Zero, 1. Let's replace this one by g and then enter. The answer is after 5 iteration we have 0.588. So let's graph this one first. Okay, let's graph our function. Let's this most graphing calculator, and then we have sine x minus e to the negative x. Okay, so in the interval 0, 1 we have this root here. Okay, in the interval 0, 1. So 589, 0.589. So, but based on our computation, this one here, 588. We have here 589, rounded to 3 decimal place. So this is the correct value. Okay. How about for the second, for the Newton's method? Okay, let's try the Newton's method. Let's open a file. Where are you? Newton's method, this one here. Okay, let's run this code first, and we have copy this one, import, and then also this function. Okay, enter, and then we have to copy this. Copy. Okay, so let's replace this one by g, and then what's the derivative of our starting guess is 0. Our tolerance is 1 times 10 to the negative 4. Now our iteration is 20. So let's get the derivative of the function first. Let's go to our open board. Let's have this new page. Okay, so this is our function. Example 36. F of x is equal to sine x minus e to the x, e to the negative x. So the derivative is f prime of x is equal to derivative of sine is cosine minus derivative of e to the negative x is e to the negative x, then the derivative of, e to the, of negative x is negative 1. So if we are going to simplify this one, we have cosine x plus e to the negative x. Okay, so that's the derivative of sine x minus e to the x. So let's go now to our IDLE, Python IDLE. This one here is I have to cut this first, and let's say g prime is equal to lambda x is equal to np dot cosine x plus np dot axp to the negative x, and hit enter. Okay, paste and replace this one by g, and then you have to delete the colon and then hit enter. So the answer is it differs at what digit? 27434, this one here 43. So this point. So correct up to 1 2 3 4 5 6 7 8 decimal place, but the iteration is 4 for the Newton's method and 5 for the second method. Okay, so let's answer F1. Let's go to our PDF. Okay, using the Python codes for the second and Newton's method to find solutions, set tolerance, and then do a visual inspection of the estimates and comment on the convergence rates of the methods. So I think the Newton's method is faster than the second method based on the calculation. It takes 4 iterations for Newton's method, while 5 iterations for second method to get the root of the equation sine x minus e to the negative x is equal to 0 at the interval 0 1. Okay, so this is your problem set number 3. Example 3. No, this is problem set, sorry, this is not an example. I'm going to delete this one also, replace as a problem set. Okay, so just copy, and this one here also we have A, B, and C. Okay, so I'm going to replace this one first. Okay, so So as you have noticed, I already changed the title. We have problem set number 3. For number letter A, the function y is equal to log x has a root at x is equal to 1. Run the Python code for Newton's method for with the initial guess, which is equal to 2, and the tolerance is 10 to the 4. I guess this is 10 to the negative 4. Okay, n is equal to 20, and then try also if you are using initial guess which is equal to 3. The question is, does Newton's method find the root in each case? So meaning, if you are using the initial guess 2 and 3, Python gives an error, explain what the error is. Okay, so that's for letter A. For letter B, one can combine the bisection method and Newton's method to develop a hybrid method that converges for a wider range of starting values P sub O and has a better convergence rate than the bisection method. So write a Python code for a bisection Newton method. This is the hybrid method, combining Newton's method and bisection method as described below. So you can refer to your lecture notes. Your code will input the function, the first derivative, the interval AB, the endpoint, the tolerance, and the number of iterations, where f and f prime are its derivative, function is derivative. Also the interval AB that contains the root, this one here, in bisection method. And as I've said, epsilon is the tolerance and n is the number of iterations. The code will use the same stopping criterion used in Newton's method. The method will start with computing the midpoint AB, so be careful, and call it P sub O, and use the Newton's method with initial guess P sub O. So meaning to say, the midpoint of the midpoint in the interval AB is our initial guess, and that's for this value here. The midpoint is for the Newton's method to obtain P1. It will then check whether P1 is an element of this interval. If P1 is in the interval, then the code will continue using Newton's method if it is in this interval. And compute P sub 2. If this P1 here is not an element in the interval, then we will not accept P1 as the next iteration. Instead, the code will switch to the bisection method, determine which subinterval among this one here, A, comma, P sub 0, P sub 0, comma, B. So P sub 0 is the midpoint that contains the root. Updates the interval AB as the subinterval that contains the root and sets P1 to the midpoint of this interval. So once the P1 is obtained, the code will check if the stopping criterion is satisfied. So you will put the stopping criterion just like in the Newton's method. If it is satisfied, the code will return P1 and the iteration number and terminate. If it is not satisfied, the code will use Newton's method with P1 as the initial guess or new initial guess to compute for P2. And it will check whether P2 is an element of this interval and continue in this way. If the code does not terminate after n iterations, output an error similar to Newton's method. So this hybrid method that you code in Python, IDLE, or in Anaconda, apply this hybrid method to a known polynomial. So each of you must have different polynomial. So if ever if there is a one among you that don't have the same polynomial, then automatically you will have a 0 in this problem set. and check if the method finds the correct root. And also apply to y is equal to log x in part A with the interval 0, 6, for which the Newton's method failed in part A. So you already have a guess in problem set 3A. Okay. Letter C, do you think in general the hybrid method converges to the root, provided the initial interval AB contains the root for any starting value feasible, and explain that one. Okay, so that's it for the second method. I will also ask a question just like the Newton's method, to where does the function or the given will fail. I'm going to ask that one in the ed puzzle. So for our next topic, we will discuss, this is the last one, fixed point iteration, and we are done with chapter 2. Okay, so that's it. Thank you everyone for listening. God bless.